Floyd Warshall algorithm. Floyd Warshall algorithm is a dynamic programming algorithm which is used for finding shortest path between all pairs of vertices in a weighted graph. So previously we learned about Dijkstra's algorithm and then Bellman-Ford algorithm. What were these algorithms used for? These were both single source shortest path algorithm. That is, from one source vertex, you will find shortest path to all other vertices that are present in the graph. This is what single source shortest path algorithm is. Dijkstra's algorithm as well as Bellman-Ford algorithm, both of these were of the same category. But coming to Floyd Warshall algorithm, this is an all source shortest path algorithm. From every single vertex, you will find shortest path to all other vertices. This is the speciality of Floyd Warshall algorithm. So if you want to find the shortest path from one vertex to all other vertices, use Dijkstra's or Bellman-Ford. But if you want to know shortest path from all the vertices to every other vertex, then you will go for Floyd Warshall, right? Let us see how this Floyd Warshall algorithm works and what are the specialities of this algorithm. First thing you have to understand is Floyd Warshall algorithm, it works both for directed as well as undirected graphs. In both cases, you can use Floyd Warshall algorithm. Secondly, this can handle negative weight edges. In case of previous cases, that is Dijkstra's and Bellman-Ford, we had seen that Dijkstra's doesn't work on negative weight edges, but Bellman-Ford works on negative weight edges. Coming to Floyd Warshall, it can handle negative weight edges. This is a speciality of Floyd Warshall. Keep in mind, there should be no negative weight cycles. If there are negative weight edges, it can be handled. But if there are negative weight cycles, then it cannot be handled. This we had seen in previous lectures that if there is a negative weight cycle, then it's not possible to find the shortest path. That is why it cannot handle negative weight cycles. But in case of negative weight edges, it is fine. Floyd Warshall can handle this. This is the basic you have to understand. Next thing is, what is the key idea behind Floyd Warshall algorithm? How is it working? It's a very simple idea. The idea is like this. You have to build the solution incrementally. That is, step by step, you will build the solution. What will you do in each step? In each step, you will pick one vertex as an intermediate vertex. What are you going to do then? For each pair of vertices that are present in your graph, for every pair of vertices, what will you do? You will consider this vertex as intermediate vertex and see if usage of this as intermediate vertex will decrease the path between those vertices. Let us say you have a graph something like this. There is A, B, C, D and E. These are the vertices. If you want to find distance between all these by considering B as intermediate vertex, what will you do? Let us say you are considering edge AD now. If you want to find edge AD, there is no edge, but I am saying shortest path from A to D. For that, you will see if with B as intermediate vertex, can you find a path that is shorter than the existing path? Let us say for now, there is no direct edge. And let us consider that the distance from A to D is infinity. If this is the case, and if this weight is 2 and this weight is 3, by considering B as intermediate vertex, you have a path which says you can go AB and then BD, which gives you AB is 2 plus BD is 3, so a total of 5. This 5 is smaller than infinity, because of which you found a shorter path which is having a total weight of 5 to go from A to D considering B as intermediate vertex. Similarly, for A to E also you will try. How will you try from A to E? You will do AB plus BE. So in this case, AB is 2. BE does not have a direct edge. But what happens is, when you proceed with this algorithm, Sometimes, let us say by this point, you would already have some distance that you found from BE. So for example, here you found for AD. Next time, if you are using, let us say, D as intermediate vertex, in order to find distance AE, what will you do? In that case, it will be AD plus DE. Previously, when using B as intermediate, you already found that AD is 5. This time, you can use AD as 5 even though there is no direct edge from A to D. Plus, let us say this DE is 1. In that case, this will be 6. This is how you will consider each vertex as intermediate vertex and then keep finding the shortest path for all pair of vertices. This is the basic idea behind Floyd Warshall. So how do you move step by step here? Let us say in the first step, you are taking vertex number 1 as intermediate vertex. Using vertex number 1 as intermediate vertex, you will find shortest path for all the pairs of vertices. Okay. After this, in step 2, you will move to vertex 2. This time, vertex 2 is your intermediate vertex, and using this, you will try to find shortest path for all pairs of vertices. Similarly, then you will move on to vertex 3 and so on till the last vertex, the nth vertex, let us say. When you reach the last vertex, you know, you have already considered all vertices as intermediate vertices and you calculated the shortest path for all pairs of vertices. This is when your algorithm stops. One more thing, one very important point that you have to understand is, when I say, let us say, third vertex as intermediate vertex, it doesn't mean that I'm just considering third vertex. It means I'm considering all the vertices that I've considered till this point. That is, when I say number 3 as intermediate vertex, I'm actually saying considering vertex 1, 2 and 3 as intermediate vertices. That is, using these 3 vertices as intermediate vertex, if there is a path from vertex A to vertex B. This is what I will try. So at the point when I'm saying N as the intermediate vertex, that is the last vertex, at this point I am considering all the vertices that are present in the graph as intermediate vertices, which means using all the vertices that are present in the graph, which is the shortest path to go from one vertex to other. This is what I am trying to find here. This is the basic idea behind Floyd Warshall algorithm. Let us just see what steps are to be followed in order to complete this algorithm. Okay. With this, you will have clarity on how this algorithm is working. Okay. So these are the steps to be followed. First thing is, you need a distance matrix. This matrix is what we are going to update. So there will be a distance matrix D in which any particular entry Dij, what will this represent? Any particular entry Dij, this represents the shortest distance from vertex I to vertex J. This is your distance matrix. So if you have n vertices in total, this will be an n cross n matrix in which every single entry Dij will represent the shortest distance from vertex I to vertex J. This is the logic. What will be the initial values in this distance matrix? Let us say for Dii, for every entry Dii, here you are going from same vertex to the same vertex. So there is no distance here. So this will be equal to 0. This is the first condition. Second condition is, if you have any Dij which is having a direct edge, in that case, the weight of the edge Wij will be the value populated in Dij. Here I am talking about the initial values. That is, before you start with the algorithm, what initial values should you populate in distance matrix? Okay. What if there is no edge between I and j? In that case, you should put Dij is equal to infinity. This is when there is no edge between I and j. So this is the initialization. If there is an edge, then you will put the weight of edge there. If there is no edge present, you will put infinity. And if it is the same vertex, if it is Dii, you will put it as 0. These are the initial values in distance matrix. Next thing, what are you going to do when you consider each vertex as the intermediate vertex? So this is the next step. For each intermediate vertex, for each k, where when I say k, this k is an intermediate vertex, or I'll write here. For each intermediate vertex k, what am I going to do? Here you have to keep in mind this will run from 1 to n, or let us say 1 to v. So k will take all values from 1 to v in order. So for each intermediate vertex k, what should I do? For each pair of vertices, I should update values by considering k as intermediate. So for each intermediate vertex k, inside this, I should take for each pair uv, or let us say ij, whatever you can take, each pair of vertex ij. This means I am considering this edge as going from I to j, not necessarily edge. I am taking shortest path from I to j. Okay. So for each pair of vertices ij, what should I do? I should consider k as intermediate vertex and see if a shorter path is possible. How will I do that? We already learned this. That is, I will update distance from I to j this as minimum of one is whatever is already existing, that is dij. If this itself is the minimum value, then this will stay as it is. Otherwise, what should I consider? I should take I distance from I to k, which is my intermediate vertex, plus distance from, I'll write here, okay, this plus distance from k to j. So here I am considering k as intermediate vertex. Minimum of either the value that is already present dij, or I'll put this here dik plus dkj. These two options are there. If the existing value itself is the smallest, you will keep it. Otherwise, you will try to use k as intermediate vertex, then find distance from the source vertex I to k, and then from k to j. If that is smaller than the existing value of dij, then you will substitute dij with that value. This is the logic. This logic you have to run for all the pair of vertices, and that should be done for all vertices by considering those as intermediates. Okay. So again, keep in mind, whenever I say considering vertex k as intermediate, at that point you are actually considering all vertices from 1 to k as intermediate. Okay. That is how this algorithm is proceeding, because in the previous iterations you have already considered each vertex from 1 to k minus 1. So when you consider k, automatically you are considering all the vertices from 1 to k minus 1. Okay, because your distance matrix is already having values which are updated considering all the vertices from 1 to k minus 1, and you are newly considering k, which means you are considering all the vertices from 1 to k, right? Keep this in mind. This is the most important logic. This is where you understand that when you reach last vertex, vth vertex, by this point you are considering that all the vertices can act as intermediate vertices. Then what is the minimum distance possible for every pair of vertices ij, right? So this is the logic behind Floyd Warshall. One more thing, at the end, what happens? At the end of this algorithm, your distance matrix D, this will have the shortest distance between all pairs of vertices. This is the logic behind Floyd Warshall. Let us see, one important thing is, how can you detect negative weight cycle here? I told you beforehand that Floyd Warshall algorithm, this has the ability to detect negative weight cycles. Negative weight edges, it can anyway handle, it will find the shortest path. But if there is a negative weight cycle, then Floyd Warshall algorithm will be able to detect it like Bellman-Ford. But the question is, how is it going to detect? In case of Bellman-Ford, we had seen that we have to do one additional iteration, and if the values change, you will say there is a negative weight cycle. But in case of Floyd Warshall, you don't have to do an additional iteration. Instead, you just have to take a look at your distance matrix that is finally returned. And in this distance matrix, if there is any value dii, that is same vertex dii, if dii is less than 0, in this case, you can say there is a negative weight cycle present in the graph. How am I saying there is a negative weight cycle present if dii is less than 0? The reason is, if there is a negative weight cycle, let us say somewhere in the graph there is a negative weight cycle. Let us say there is a cycle here. This cycle, let us say, is a negative weight cycle with values -1, 2 and -2. So totally it is -1. So this is a negative weight cycle. For any vertex that is involved in this cycle, take this vertex or this vertex, for those vertices, distance value will be less than 0. Because of that is final distance matrix after all the Floyd Warshall algorithm is applied, it will be less than 0. Because of that, you can say that if any of your dii, the distance from same vertex to same vertex, this by default it should be 0. Because you are not going anywhere, you are staying in the same vertex, this value has to be 0. If it is less than 0, that means there is a negative weight cycle present in this graph. Then you should say that shortest path finding is not possible because there is a negative weight cycle present. This is it about Floyd Warshall. One more thing. What about the time and space complexities of this algorithm? Well, we'll just see the steps that we have written and we'll try to understand time and space complexities. All these steps, these are all just updation of this matrix. So the size of matrix is v square. So it will take order of v square time. Why is it v square time? Because you have v vertices. You are having a matrix which is of size v cross v. So updating all the values as per this, it will take order of v square time, right? This is the time for initial updation. After that, for each intermediate vertex k, so here you are taking each vertex, so order of v time, plus for each pair inside this, for each of the vertex, you are considering each pair. How many pairs of vertices will be there? If v vertices are present, then there will be v square pair of vertices. So this will be order of v square. So order of v times, you are running order of v square different pairs. This operation, this is an order of one operation, it won't take time. So main time complexity is consumed by these ones. These are the main contributors to your time complexity. Order of v times, you have to enter this loop. Inside that, you are running another loop which is running order of v square times. So what is the total time complexity? Total time complexity will be order of v square into v, which is order of v cube. So your time complexity of Floyd Warshall algorithm is order of v cube. What about the space complexity? In case of space complexity, the only additional space that is used is for this distance matrix. What is the size of the distance matrix? If you have v vertices, your matrix, distance matrix, is a v cross v matrix, which means space complexity is order of v square, right? So time complexity is order of v cube and space complexity is order of v square.